Now I will do a small calculation of an attempt to derive this Feynman's path integral statement from our usual way of doing quantum mechanics, from usual um, so from usual Schrodinger theory. So let's discuss a more concrete understanding of path integral. More concrete means whatever we know how to calculate in Schrodinger theory, using that. So the question is that how to derive using usual Schrodinger theory. That is the question. Okay. Okay, so to answer this question, so first recall from the definition of the state x comma t that x hat of t acting on x comma t will be x comma t, where x hat of t is the Heisenberg operator. So therefore x of t is equal to e to the power I h t over h bar x hat e to the power minus I h t over h bar, where x hat is same as x hat at t equal to 0. Similarly, this gate has a time evolution which is given by e to the power I h t over h bar acting on x, where this x is nothing but x at time t equal to 0. So it means that this equation implies now at a particular time t, the operator, the Heisenberg operator, has eigenvalue x. Now if you go to t equal to 0 and you take the corresponding Heisenberg operator and the corresponding, that is the corresponding Heisenberg operator and the corresponding state, then that operator has the same eigenvalue x, right, which you can easily check e to the power I h t over h bar x hat e to the minus I h t over h bar acting on x comma t. This is nothing but that x we defined here. So this is e to the power I h t over h bar x acting on x. But at the same time, it must be the right hand side, which is x times, right hand side is this x times x t, but xt, but this xt is same as this operator acting on this. So therefore we must be having x hat acting on x is equal to x, right? Anyway, this is how you can do the manipulations, and you can use the same time evolution operator to calculate the matrix element. So calculate the matrix element xftf xi comma ti to be equal to xf e to the power minus I over h bar h Tf minus Ti acting on Xi. And then again, Tf minus Ti can be written as n times epsilon, where n is large and epsilon is close to zero, going to zero. So this is n going to infinity, n epsilon going to Tf minus Ti finite, Xf e to the power minus I over h bar h hat in epsilon Xi. And this operator can be written as a factor of the time evolution operator h hat epsilon to the power minus I by h bar h at epsilon n times, right? And then you can insert between this here and here the identity operator, the completeness relation. So this gives you, limit n tends to infinity, n epsilon goes to Tf minus Ti, integral dx1 to dxn minus 1, xf e to the minus I by h bar h at epsilon xn minus 1 xn minus 1 e to the power minus I by h bar h at epsilon xn minus 2 and so on up to x1 to x1 to the power minus I by h bar h at epsilon xi. So now one has to calculate this matrix element, each one of them. This can be calculated in the following manner. So calculate xn plus 1 e to the power minus I by h bar h hat epsilon xn. Since it's epsilon is infinitesimal, you can approximate this is same as 1 minus I by h bar epsilon h hat xn. Okay. And then you see the first term can be calculated easily because it's just the overlap of xn plus 1 and xn. But the second term has h hat sandwiched between xn plus 1 and xn. And in order to do this, we will describe these matrix element in a particular fashion where so let me first write it down and then explain. So integral, so insert a momentum space identity operator xn plus 1 pn, then pn 1 minus I over h bar epsilon h hat xn. Now define a classical function h pn comma xn to be pn h hat xn divided by pn xn. Okay, then using this you could write the entire result as dpn e to the power minus I by h bar epsilon h pn comma xn xn plus 1 overlap pn overlap xn. Now you can use the standard expression of this overlap, which is 1 over square root 2 pi h bar times the phase e to the power minus I pn xn over h bar. Okay, if you do that and use x dot n to be equal to xn plus 1 minus xn divided by epsilon. Okay, so limit epsilon goes to 0. Okay, so this is x dot n. Then using these two, you can get the final result to be integral dpn over 2 pi h bar, okay, e to the power I by h bar times epsilon pn xn dot minus h pn xn. Okay. For small epsilon. Okay, so this is for small epsilon. That is the result, and therefore when you use this result for this matrix element here, which is given by this, back into this expression here. Okay, then you see that in this expression you already had the integral over x, and now you have an integral over p, which is coming from each factor like this. Okay, so the final result therefore is xf tf xi ti is equal to limit n tends to infinity, n epsilon tends to tf minus ti integral dx1 to dx n minus 1 dp0 by 2 pi h bar to dp n minus 1 by 2 pi h bar times exponential I epsilon over h bar times small n equal to 0 to n minus 1 pn xn dot minus h pn xn. So this is a path integral over the phase space, or it's also called Hamiltonian path integral. This is sometimes called Hamiltonian path integral. Just like before, you could also write it as integral dx path integral dp e to the power I by h bar integral dt ti to tf px dot minus h xpt. Or maybe we should take this time independent Hamiltonian for the time being. Okay, so so from the using the Schrodinger theory, we therefore derive the same matrix element to be of this form, where we have a Hamiltonian path integral or phase space path integral. On the other hand, Feynman gives you an expression which is a configuration space path integral, where there is no momentum integral. And we shall next discuss how these two, this one and Feynman's proposal, could be related. Okay, so that's the end of today's discussion.